Hi everybody. Today we're going to be learning a little bit about strong ground motions and ground motion parameters. This is an important topic related to earthquake engineering, and it transcends all the different branches of earthquake engineering, but particularly is applicable to structural engineers and geotechnical engineers that want to do time history analysis or predict some sort of response or behavior from strong ground motions. So ever since the very first earthquake time history was recorded in 1940 with the El Centro record, we've been trying to develop ways that we can quantify the earthquake. And it's really, really tricky because there's lots of different things that we can measure in the earthquake time history. So how do we effectively quantify it? So pretty early on, we started turning to our friends, the electrical engineers, and maybe you can figure out the reason why. What are electrical engineers really good at? Well, they're really good at working with waves. And earthquake records or earthquake ground motion recordings resemble wave signals, and so we can take some of the principles and things that they apply on a regular basis and apply those principles to earthquake waves. So the process of breaking down and interpreting a recorded earthquake wave, or any wave for that matter, is called signal processing. So let's get down to the nitty-gritty though. How in the world do we record earthquake motions, like the 1940 El Centro record or any of the thousands of motions we've recorded ever since? So the early recording instruments are what we call seismographs, and these are the things that you kind of think of when you think of an earthquake recording instrument. You know what I mean. The rotating barrel has paper on it, and then you got a little pen that's kind of scribbling on the paper, and then if the ground shakes and the pen starts to move. A seismograph is that kind of instrument. So we have this mass or this weight that I'm circling in red, and if the ground moves or shifts back and forth, it's going to cause that mass to accelerate and want to rock back and forth. And then you have a spring, of course, that always wants to bring it back to its normal position. And on the bottom of this weight, you have a pin that's on the rotating drum. And so we could correlate or calculate the amount of movement of the mass to the acceleration or the displacement or the velocity, whatever we needed. And so that's how we used to record ground motion records. Today, most of the ground motion records are recorded not with seismographs, but accelerographs. So this is kind of a common misconception because a lot of people, even myself included, are going to say seismograph, seismograph, seismograph. But what we really mean is accelerograph. So accelerographs use accelerometers, like what's in your digital phone, for instance. Today, these instruments are really sophisticated. They've moved from analog instruments to digital instruments, and the instruments can sample up to about 1,000 times per second. So in other words, it's just hitting readings and providing acceleration readings maybe at anywhere between 200 to 1,000 times per second. So a seismic network is a group of ground motion recording instruments that are networked together and share information. So if an earthquake happens anywhere, we can record it, observe it, and study it. So here in the United States, the big seismic network that we have, it's a conglomeration of all different universities, geological surveys, etc. It's called the American the American Network of Seismic Stations, ANSS. That's what that stands for. And ANSS has what they call the Backbone National Network. Here's a little map of it right here, and you can see that by backbone, what this means is these are kind of the primary base ground motion recording stations located all throughout the country. And so any ground motion occurs anywhere, we can generally pick it up and read it. Globally, ANSS is part of a larger global network called the Global Seismic Network, or GSN. And this, imagine networks similar to ANSS, but in other countries. Europe has their own network. Chile has its own network. Japan has its own network, or multiple networks. And these networks, more often than not, belong to the GSN. Here locally in Utah, we have the University of Utah seismograph stations, or UUSS, and they're the organization that instruments most of the region, at least the state of Utah, most of eastern Idaho, a lot of western Wyoming, and the Yellowstone area. That's run by the University of Utah. Hopefully, when we go on our field trip in the spring, we're going to go visit the seismograph stations up at the University of Utah, and they can show us some really cool stuff. So lots of times if we record an acceleration time history, we can get small errors from lots of different things. But one of the most common sources of error is what's called the triggering acceleration. So the triggering acceleration is the minimum amount of acceleration required to get the instrument to start recording. And so you can have the instrument set to different sensitivities, but you can imagine that this would be kind of a tricky thing, because if it's too sensitive, it might start recording every time a truck drives by or something like that, thinking it's an earthquake. But if it's not sensitive enough, an earthquake may happen and the instrument may not recognize it, may not record it. But because of this triggering error, often this is going to result in a linear error in the velocity record. Because remember, velocity is simply the derivative of the acceleration, and a quadratic error in the displacement. And so, because again, we're going to not the derivative, I'm sorry, we're going to integrate. It's the integral. Velocity is the integral of acceleration, and displacement is the integral of velocity. So if we have some error in the acceleration, like a constant error, we get linear error in the velocity and a quadratic error in the displacement. And you can get some really freaky looking plots, like the plot down here, where you can see I have a velocity record versus time, and you can definitely see that we're getting some drift, that with time the velocity time history is moving down, down, down. So in general, we can correct these types of errors with what's called a baseline correction. So in general, we just subtract out the constant error in the acceleration, and then reintegrate it, and we correct the velocity and the displacement. Now, what about errors that aren't constant in the acceleration? We definitely have those. This plot down here in the right, that's not a linear error in the velocity. That looks more like a quadratic error. So that means we have a linear error occurring in the acceleration. So when we do baseline corrections in our signal processing, we can experiment with different things and see which correction, which type of baseline correction, whether it's linear or sinusoidal, or there's lots of different corrections. We can see which one gives us the best looking plots when we're done. Another thing to consider is that, as I mentioned before, these ground motion instruments can and do often record a lot of noise. And this noise can corrupt ground motion records. Everything today emits some sort of signal because we have machines that are constantly vibrating. We have even electricity in buildings and stuff buzzes a little bit and can cause some vibrations to be picked up in these instruments. So to overcome this vibration, we have to usually filter it out or compensate for it somehow. In general, though, the most popular approach is to apply some sort of filter to our time history. So there's different types of filters. One filter is called a high pass filter, and this refers to allowing high frequency ground motions to pass. That's why they call it a high pass. But it's going to filter out the low frequency. Now we can define whatever frequency we want to filter, but usually we're going to filter out stuff less than 0.1 hertz. Another type of filter we can apply is a low pass. Now this is the opposite. We're going to remove all the really high frequency stuff, usually anything above 25 hertz. So low frequency noise generally comes from stuff that occurs really far away. I mean, we get low frequency noise from like thunderstorms occurring in Chile and stuff like that. High frequency noise is usually machinery that is contributing a lot of that really high frequency, high energy kind of excitation to the ground motion record. Now, the most common type of filter is a band pass filter. So rather than filtering twice, all we do is we do a high pass and a low pass together, and we call that a band pass. So that's going to remove both the high and the low frequency noise, and we're only going to allow to pass the frequencies that we have observed or generally associated with actual ground motions from the earthquake. By the way, another name for that type of filter is called a Butterworth filter, and when we start playing with the software Seismosignal, that's the type of filter that we'll be applying to the ground motions. So here's the 1940 El Centro record. Now we've recorded it. What in the world are we going to do with it? As I mentioned before, the real challenge is how do we quantify this time history? So as we've studied time histories now for over 70 years, we've learned that there are three significant aspects to describing an earthquake ground motion. And I've got to tell you folks that this is something that's really important, so I'm drawing my exclamation marks. Make sure you understand and know these three things. The first one are ground motion parameters that describe or deal with the amplitude of the recorded time history. The second one are ground motion parameters that deal with the frequency or what we call the frequency content of the recorded time history. And the last is a ground motion parameter that deals with the duration or how long the time history is occurring. So all three of these things are really, really important. Amplitude, frequency content, and duration. And see, the trick is that different ground motion parameters tend to describe one, maybe two of these three things. But there's only a couple of ground motion parameters that describe, in essence, all three of these categories. Let's talk about amplitude parameters first. So amplitude parameters, again, are ground motion parameters that relate specifically to how big the ground motion is. So let's go, that was from an earlier class, sorry. Let's go to our board here, and let's draw a nice flat line that we can use for our time history analysis. So now, if I draw a time history, something like that. Okay, an earthquake time history. Amplitude parameters generally deal with the peak of the time history. So whatever peak is the biggest, that's generally what we talk about when we say amplitude ground motion parameters. So the peak acceleration is the largest peak on the acceleration time history. It has some different names. The peak ground acceleration is a common name, or sometimes we call it A max for maximum ground surface acceleration. It's also called PHA for peak horizontal acceleration, or sometimes we'll use PVA, which is peak vertical acceleration. But all of these things generally refer to the same principle. We have an acceleration time history, and all we're doing is we're taking the largest acceleration, whether it's positive or negative. We're just taking the largest absolute value of the acceleration, and that's our peak acceleration. A similar thing, by the way, I do want to say that the peak acceleration tends to be governed by high frequency ground motions. The peak velocity is similar to the peak acceleration, but we're looking at the velocity time history now. So the peak velocity is often called the peak ground velocity, or PGV. Sometimes it's called Vmax, or PHV for peak horizontal velocity. These tend to be governed by the intermediate frequency ground motions. And so these are often used instead of PGA if we're dealing with structures that have longer natural periods or lower natural frequency. So these might be like bridges or tall buildings, those types of things, because those types of structures respond more closely to the velocity record of the time history instead of the acceleration time history. High frequency structures correspond better with the acceleration time history, not so much the velocity time history. Peak displacement, we can't leave that one out. We often call this the peak ground displacement, or PGD. It's not as widely used because it's governed by really low frequency ground motions. So this is the appropriate type of ground motion parameter for the design of very high period structures, such as really long bridges, really tall buildings, or maybe water tanks where we have sloshing going on inside of the tank. There's a couple other less used parameters. For instance, the effective acceleration, the effective design acceleration, the sustained maximum acceleration or velocity. I don't even know what those are, so that tells you we really don't use them very often. Now, amplitude parameters are nice and they're popular because they're easy. They're easy to understand. They're easy to obtain. And for that reason, a lot of people like to use them in different design applications. So for instance, if you're designing the equivalent horizontal force from an earthquake on a building, generally you're going to take the mass of the building and multiply it by the peak ground acceleration. Mass times acceleration equals force. And when we look at soil liquefaction, we're generally looking at peak ground acceleration. But there's a problem with amplitude parameters, and these two plots demonstrate it really, really well. I have here two plots from two different earthquakes plotted on the same scale. One earthquake on the left, you can see, had some high frequency ground motions, and then it had a huge peak, and then came back down and calmed back down a little bit. The ground motion on the right had this approximately the same peak. In fact, it might even be a little smaller than the ground motion on the left. So here's the question I have for you. If you look at these two plots, which one has the larger peak acceleration? You'll probably say the one on the left. So you would automatically assume that that's the worst ground motion of the two. But that may not be true, because if you look at these two plots, the plot on the right generally has more energy associated with it. So if your structure was hit by the ground motion on the right, it would likely be more damaged than if it got hit by the ground motion on the left. But when we rely on amplitude parameters alone, we often miss that fact. So that brings us to frequency content parameters. So frequency content, folks, is like the resonance. This is where everything has a natural frequency. Everything, even you, has a natural frequency. And the trick is, trying to find what the natural frequency or the frequency content of the ground motion is going to be and seeing if that's going to cause anything to resonate. So again, frequency content is going to describe how the amplitude of a ground motion is distributed across a broad range of frequencies or periods. Now, the most common set of frequency content parameters is going to involve the use of what we call a spectrum. So this is a series of parameters across a broad range of periods. The most common spectrum is called, well, it's not the most common today, but it's a very common and widely used spectrum. It's called the Fourier spectrum. And again, this comes from our electrical engineering friends. The Fourier spectrum comes from the Fourier series, which breaks down a complex wave signal into a summation of a whole bunch of simple harmonic sinusoidal waves. So in other words, we can take any really, really complex wave signal and break it down into a series of these harmonic waves that if we add them together, we get the complex wave. That's the entire basis of the Fourier spectrum. Then the Fourier spectrum then is basically what it's doing is it's telling us the amplitude or how much contribution is coming from each period of the uniform sinusoidal wave. And I know I'm probably speaking Greek to you, so it's easier if I just show you an example. So let's say that I have this wave here, wave number 1, and it has a frequency, a circular frequency of omega 1. So A here is the amplitude of the wave, and you can see, I apologize, you can see the period of the wave. It looks something like this. So if I were to try to break this down in all of the fundamental waves that comprise this one wave, you can see that, wow, we could just take a simple sine wave and represent this whole wave with one sine wave. So if I were to plot the Fourier spectrum, we would see a spike right at omega 1 with the frequency of that one wave. And the amplitude of that that spike is a function of the amplitude of the actual wave in the target wave that we're analyzing. So let's look at a different wave. Wave number 2. Now this has a different frequency. It has a higher circular frequency. We'll call it omega 2. So if I'm going to plot the Fourier spectrum for this wave, again, we can describe this wave with a single sinusoidal wave with a frequency of omega 2. And so the Fourier spectrum for this wave would just be a single peak at omega 2. Now, wave number 3 is a little tricky. It's simply the addition of wave number 1 and wave number 2. So you see it's a little more complex. So if we were to break this wave down into its individual sinusoidal components, we would have one wave that's at frequency omega 1, and we'd have one wave at frequency omega 2. And each of those waves would have its amplitudes. So the Fourier spectrum for this wave would simply be something like this, because it's telling us that we can represent complex wave number 3 with two simple sinusoidal waves, one at omega 1 and one at omega 2. So that's the idea behind a Fourier spectrum. So when we apply a Fourier spectrum to an actual transient ground motion, so something that's a lot more complex than the waves that we were just looking at, they tend to look something like this. But we learn a lot from these Fourier spectra. Because, for instance, I have here two ground motions that were recorded from the 1989 Loma Prieta earthquake. Gilroy number 1 was recorded on a rock about 22 kilometers from the epicenter of the earthquake. Gilroy number 2, this ground motion was recorded on soil, so a material that is not nearly as stiff as rock. and it was recorded at a distance of about 23 kilometers from the epicenter. So the distance is about the same. But look how different these Fourier spectra are. The spectrum that was recorded on rock has a lot of peaks at the low period high frequencies. This means that this tends to be the frequency that corresponds to the rock. It's like the natural frequency or natural period of the rock. So these are the frequencies that the rock is really transmitting efficiently to the ground motion recording instrument. All of these other periods out here, the high period stuff, the rock is not transmitting it efficiently. It tends to filter it out. But look what happens in the soil. In the soil, the high frequency stuff kind of gets filtered out. But what really gets transmitted well is the stuff that's at a period between 1 and 2 seconds, because that corresponds to the frequency of the soil. So it transmits ground motions that have that frequency really, really efficiently. So hopefully this gives you a little idea of why Fourier spectra are useful. They give us an indication of which ground motions or the frequency of the ground motions are getting through. So remember, rock has higher amplitudes at low periods and soil has higher amplitudes at high periods. Now, something that's similar to a Fourier spectrum, but a little different, is called a response spectrum. Now, the Fourier spectrum is useful, but it focuses on the amplitudes and the frequency content of the time history, or the ground motion itself. And that's nice, that's the incoming ground motion, but we're a little more interested in what the response of a structure might be. And so engineers might want to know what the structural response would be to those time histories. A response spectrum basically analyzes a series of hypothetical single degree of freedom structures and plots the maximum response of each of those structures to the ground motion that we're analyzing. So in other words, we're just pretending that we have structures of all different natural periods, and we're going to plot the maximum response, and maybe in terms of acceleration or displacement or velocity, from each of these structures as we expose them to our time history. The thing that's important about response spectra is that we have to specify a level of damping associated with our structure. Because when you start to rock a structure back and forth, it starts to eat up some energy, and there's always going to be some damping. So we do have to specify a level of damping. Usually that's going to be about 5% for most undamaged structures. Oh, look at that. So here's how I like this little scenario here. It helps us kind of picture what's going on. I have here a table, okay? Imagine I have a table, and on this table I have 3 different buildings. Now they all have the same mass, mass M, mass M, mass M, mass M, mass M. The only thing different about each of these little buildings is the stiffness, because each one of these has a lower and lower stiffness because they have a taller and taller height. So that means that each one of these buildings is going to rock at a different natural frequency. And so if I shake the table on which all of these buildings are attached, they're each going to rock according to a different frequency. Now, if I go ahead and I plot the response of each of these masses as I introduce each one to the same input ground motion, as I plot then that response of that mass, and I take the peak response, and then I plot that peak response as a function of the natural period of each of these buildings, then what I get then is a function that gives me the peak response versus natural period of a hypothetical single degree of freedom structure. This line that results then is what we call a response spectrum, and it represents the amount of response that we would expect from a series of structures or buildings. And so why these things are cool is you can analyze, say you're designing some structure, and you can estimate what its natural period is. You can then go at that natural period up to the response spectrum and estimate how big its maximum response is going to be to our input motion down here. So it takes a little bit of time to kind of understand what a response spectrum is. So I recommend that you kind of chew on this a little bit. Maybe pause the presentation, have a look at this slide, and try to understand what's going on here. So again, I want you to remember that on a response spectrum, the y-axis is the maximum value from each of our oscillators or our structures, and the x-axis is the corresponding natural period of that structure or oscillator. Okay, there's several other frequency content parameters. For instance, there's the predominant period. This is the period at which the maximum spectral acceleration occurs in the response spectrum. There's the bandwidth, and this is the range of frequencies over which some level of the Fourier amplitude is exceeded. And so we can derive and show that it's usually 1 divided by the square root of 2 times the maximum amplitude. There's other central frequency, shape factor. This one is actually quite heavily used. It's the maximum or the peak ground velocity divided by the peak ground acceleration. If you do the units on this, what you end up getting is units of time, I believe, like a period. And so you can see how this then would relate to frequency content. Then you have the mean period. Okay, let's talk finally about duration ground motion parameters. So duration ground motion parameters deal with how long the earthquake is occurring. One of the most common duration parameters is called the bracketed duration. So the bracketed duration is the length of time between when an earthquake first exceeds some triggering acceleration to the last time it exceeds that triggering acceleration. So for instance, let's say that I have a triggering acceleration of 0.05 g. And here's this time history. So this is acceleration on this axis. Okay, so I'm going to draw my brackets here of positive 0.5 and negative 0.5. So then what I'm going to do is I'm going to look in the instance that the time history first exceeds that bracket, crosses that threshold. And you can see after it crosses it for the first time, it's crossing it multiple times all through here. I mean, it's crossing it, crossing it, crossing it. So that's fine. We're just letting it do its thing. We're going to find the very last instance that it crosses our bracket or our threshold acceleration. This bracketed period, this length of time right here, is what we call then the bracketed duration. Now we can define these triggering thresholds to be any acceleration, but most commonly this is usually 0.05 g. Bracketed duration is usually represented with a t sub d. Another duration parameter that we can use is the equivalent number of cycles. So this is trying to relate earthquake cycles to equivalent cyclic triaxial shear test cycles. And it all relates to the amount of energy that's being put into the soil. So there's been lots of different studies out there. We're not going to focus too much on these, but you can see that for different earthquake magnitudes, we have a different number of equivalent significant stress cycles. So if we have a magnitude 8.5, for instance, we would expect that earthquake to last a pretty long time. You can see it's the equivalent of 26 cycles in a cyclic triaxial test. Now, what about ground motion parameters that account for all, or well, let's say more than one of the important attributes of a ground motion, namely amplitude, frequency, content, and duration? So there's a couple of ground motion parameters that deal with more than one, and in fact the ones I'm going to show you generally deal with all three. One very popular parameter is called the Arius intensity, and all this is a quantification of the amount of energy in the ground motion record. If I want to look at Arius intensity, all I'm going to do is I'm going to sum up the area beneath each one of these little curves here. I'm going to sum it up all the way. And then so what ends up happening is if I plot Arius intensity as a function of the time history, Arius intensity starts building with the time history and eventually tops out. When we can plot it in terms of absolute Arius intensity, or we can plot it in terms of a normalized or a percent Arius intensity, so that by the time it reaches the peak, it might be at 100%, and at the bottom it's 0%. Or we can actually show the actual computed Arius intensity. So here's the equation for Arius intensity. You can see where we get that. Now the significant duration, this is another duration parameter, is the amount of time it takes to integrate from an Arius intensity of 5% to an Arius intensity of 95%, the maximum. So when I say 5% and 95%, that's relative to the Arius intensity max from the earthquake. Okay, there's another parameter called the cumulative absolute velocity, or CAV. This is similar to the Arius intensity, but it's just a simple integration of the area under the absolute accelerogram, and we're only going to integrate in the bracketed duration. So instead of squaring the acceleration and get rid of the negatives, we're just going to take the absolute value of the acceleration time history. Okay, so wrapping things up, boy, how do we compute all these different ground motion parameters? So we can get a time history record, but how in the world do we compute cumulative absolute velocity or Arius intensity? That seems like it could be a real chore to try to develop and code a way to compute these different parameters, and it is a pain. When I was going to school, my teacher made me write a Fortran code to do my own signal processing. It was no fun. I'm not that mean, and today there are a lot of different commercial programs out there that can do the signal processing of these ground motion records, and they're very user-friendly and they're easy to obtain. I like the software Seismosignal. I like it a lot because it was developed by structural earthquake engineers over in Great Britain. They did a great job. Their professors, actually, I believe at the, I want to say the Royal University of London or something like that. And they make their software available for free to you. So any student or academic that wants to use their software, all you have to do is send them an email from your academic account, and they'll give you a free license to the software to put on your own computers. So if you go ahead and download Seismosoft, you can see the directions when it tries to activate, how you can register your email address with these folks and get your own free version. I'm going to ask you folks to please get this software for your own computers. Now, if you don't have your own computer, we do have Seismosignal loaded on computers in the CADM labs, I believe. And so you can go check it out and see if it's working there. But if you have your own computer, I just encourage you to take advantage of this deal. Get the software for free. It's going to be a lot of fun. What I'm going to do now, I'm going to close this lecture and I'm going to start another lecture where I'm going to give just a little demonstration and tutorial of how Seismosignal works. So if you have any questions on ground motion parameters, shoot me an email or a message in Learning Suite, or go ahead and find me after I get back from my trip, and we'll go ahead and answer your questions. So again, thank you folks for your attention. Have a wonderful day, and I will see you later.